So now we're starting the second half of our first unit, which is dealing with accelerated motion. So before this, everything that we've been doing has been moving at a constant speed. So now we're going to make it a little bit trickier when we add acceleration to it. So anytime we have acceleration, we add Newton's second law. So Newton's first law from the first part of the unit was objects in motion stay in motion. Objects in rest stay at rest if there's no net force acting on them. Well, what happens if there's a net force acting on it? So if a net force is applied to an object, it will accelerate. Acceleration can refer to both speeding up or slowing down. Sometimes we use deceleration when we're talking about slowing down, but acceleration can mean slowing down as well. So here we have test tube guy, kicks the ball, applies a force, and the ball goes from a 0 meters per second to moving, right? So the ball accelerates. Or for slowing down, right? This horse is moving, this horse is applying friction, putting its legs like that, so there's lots of friction, and the horse goes from moving to slowing down. So both of those would be acceleration, and both of those would be a part of Newton's second law. So vector diagrams are used to give both visual of acceleration and velocity. Right? We've already done free body diagrams, but now with acceleration, we're going to add these vector diagrams. For an object that's speeding up, both velocity and acceleration are going to be working in the same direction. Okay, so let's draw a little picture here. So I'm going to show what a vector diagram would look like for an object that's speeding up. Okay. So if I have 3 different points of time, right? So here's a table, right? This is a table, or I guess that's a bad drawing. So if this is a table here, and the ball rolls off the table, sure. These are 3 different points in time. So this is when it just starts to fall. This is like halfway to the ground, and this is all the way to the ground. This is the ground right here. We can draw on a vector diagram. So as this object is falling, what we'll see is that falling objects always have an acceleration of 9.81. Right. And as objects fall, our acceleration is going to be the same. Meters per second squared, 9.81 meters per second squared. So our acceleration is the same, so we draw the same size arrow, and we're going to talk about that in a lot more detail. So just as it leaves the table, right, it doesn't have any velocity yet, so we wouldn't draw velocity on there. But what we're going to draw in the second one is that our velocity gets bigger, and the velocity is going down, right? You drop an object, you drop an object off something, and if this is down right here, it starts moving downwards. And as it accelerates, it starts going faster. So here it's not moving at all. Here it's going faster, here it's going faster. And I draw that with longer arrows. So what I want you to notice is that acceleration and velocity are in the same direction. So when velocity and acceleration are in the same direction, our velocity is going to get bigger. Okay, that's it. That's the key to this. That's what I want you to focus on right now, because we're going to do a lot more with this. So for an object slowing down, velocity and acceleration are going to be in the opposite direction. So to show an object slowing down, what we're going to do is we're going to look at something. So if I take this and I throw it up like that, we're going to look at it as it goes up. So we have these 3 locations here, and this is my hand, my stub of my hand, so it leaves my hand, and acceleration is going to stay the same. We're going to talk about that a little bit more. So we're just going to put those accelerations on. But as it's going up, well, when it leaves my hand, it has a super high speed. But what we'll see is that acceleration and velocity are going in opposite directions. So as it goes up, it slows down, right? And we know that, right? As it's going up, it's going to slow down until it stops, and then it's going to come down. So we can see velocity and acceleration are in the opposite direction, which means that my object is slowing down. Okay, so let's do a board question. We're going to use our legless dog, and we're going to draw some free body diagrams and a vector diagram of the following situation. Okay, so I want you to try your best with this one because vector diagrams are new and free body diagrams. Well, how do we draw this for acceleration? But a legless dog is being pulled by a rope on his contraption, causing it to accelerate to the right. So we're going to start with a free body diagram and an F-net equation, and then I'm going to add the vector diagram to it afterwards. Okay, so try it on your own, do your best, pause the video, see if you can do it, and then we're going to do another one right after. And yeah, if this one doesn't go well, hopefully the next one does. So my legless dog is being pulled on his contraption, causing him to accelerate to the right. So there must be some sort of force applied or force of tension to the right. So this is his contraption. If you drew on force of gravity, force normal, the same size, awesome. If you didn't, it doesn't really matter. And lots of people probably drew on a force of friction going this way, and that's fine as long as you drew it smaller. So when we write an F-net equation for this, we don't care about this stuff because it's not in direction of motion. So what we would do, we choose one of these. I'm just going to use force applied. So it's going to be our force applied is positive and our force of friction is negative. So that's what our F-net equation would look like. Okay. And it says that our legless dog is accelerating to the right. So what we can draw for a vector diagram is we can kind of draw what happens the whole time. So what you'll learn is that we always keep acceleration constant. If the forces are constant, acceleration is a constant. So as you do more of these, you'll find that the acceleration is constant. And if we're accelerating to the right, we want to draw, well, here we have a small speed, here it increases, and here it increases like that. That's what our vector diagram would look like. So our free body diagram is forces, and our vector diagram is acceleration and velocity. Let's try another one, just in case that one was a little bit confusing. So we have our legless dog and is about to crash into a wall, jams on his brakes, traveling to the left. Okay, so I want you to draw a free body diagram, an F-net equation, and a vector diagram for this situation. Okay, try your best. So let's start off with the free body diagram. So here's our legless dog. And because my legless dog is traveling to the left, I want to have a big force of friction to the right in the opposite direction as that legless dog jams on his brakes. Okay. I'm just not going to include force of gravity, force normal. They don't really matter in this situation. But I'm sure what a lot of you did is you showed a force applied in this. And whenever you put a force applied, you should be able to tell yourself, well, what's applying that force, right? A legless dog is about to crash into a wall and jumps on his brakes. So what's applying that force? Nothing in the question shows that there is anything applying a force, right? So let me show you why we don't need a force applied. So Newton's first law says objects in motion will stay in motion. So I applied a force, my object in motion stayed in motion, right? It just keeps going and going and going on a straight path. So this is my legless dog here. Once I apply a force, well, my legless dog is moving without me applying a force, right? We're not talking about when I'm touching it, we're talking about now, and it's moving. Okay, so this actually doesn't have a force applied. So when we write our F-net equation, our F-net equation is equal to our force of friction. And if we draw a vector diagram as it moves over here, okay, because our net force is to the right, that means our acceleration is going to be to the right as well. And our acceleration is always going to be constant, so you don't have to worry about that. So our acceleration is constant to the right because our F-net is to the right. So we start off with a big velocity, and what my legless dog is doing is it's slowing down. So you can see acceleration and velocity are in opposite directions, so my velocity arrow is going to get smaller and smaller as it goes along. Okay, and that's how you draw vector diagrams and free body diagrams. So free body diagrams show the forces acting on it, and vector diagrams kind of show the change as time goes on? What happens to the velocity and acceleration? So now that we are dealing with acceleration, we can use a new physics principle. And our new physics principle is physics principle number 1. And remember that this is on the back of your data booklet. So in the back of your data booklet, there's these physics principles here, and we have physics principle number 1. So on a test, I could ask a question, what physics principle are you using? Well, we are using physics principle 1 because our Fnet is no longer 0. Okay, so when there's a net force acting on an object, it will accelerate. Okay, so what requires more force to stop? A car going 10 meters per second or a baseball going 10 meters per second? Well, I hope you picked the car because the car would take more force to stop. Why does it take more force? Well, because it's got a bigger mass. So mass has something to do with force and acceleration, and this is our formula. So Fnet equals ma is one of the most important formulas that we do all year. And I can add vector arrows to it because forces are vectors. So mass isn't a vector, but acceleration is a vector. So what that means is whatever direction our net force is also the direction that our acceleration is, which we kind of did in those vector diagrams before, right? So Fnet is our net force, which is the sum of all our forces. M is our mass, and A is our acceleration. Okay, and you can find this formula on your formula sheet. It's just the very first one. Fnet is equal to ma, right there, under forces and fields. Okay, so let's do an example. Calculate the magnitude of the force acting on a 10 kilogram object accelerating 4 meters per second squared. So this is just Fnet equals ma. This is the easiest type of question you can get. Your mass is 10 kilograms. Your force or your acceleration is 4 meters per second squared. So if I want to find my net force, it would be 40, and force is in newtons. Okay, super easy, but they're not all that easy. We're going to get much harder than that. So this is more of an example that you'll see. So we have a 100 Newton force is applied to a 10 kilogram object. The force of friction between the object and the surface is 20 newtons. Determine the magnitude of the object's acceleration. So in doing questions like this, and they're talking about multiple forces acting on something, it's really important that you start with a free body diagram. And that's what we're going to do. We're going to draw a free body diagram for this situation. So we have a 10 kilogram object. And it says 100 Newton force is applied to the object. It doesn't say which direction, so I'm just going to make it to the right. And the force of friction between the object and the surface is 20 newtons. So I'm going to draw a smaller arrow this way. That's 20 newtons. Okay, determine the magnitude of the object's acceleration. So we also have force of gravity and force normal, but they're the same. They don't really matter. We want to focus on the direction of motion. So after I draw my free body diagram, I will write an Fnet equation. This is my force applied, and this is my force of friction. So I'm going to make this positive, I'm going to make this negative, so I can say force applied minus my force of friction, right? It's actually plus minus, but that's the same thing as just going minus, so I'm just going to save a little time and do the minus. So now what I'm ready to do is I'm ready to break these formulas down. So I can break any of these down because the question's asking for acceleration, but there's no acceleration in here. So Fnet is equal to ma. So instead of writing Fnet, I can write ma. And I have values for these, so I don't want to break them down, and I can't really break them down yet, so I'm going to leave them as is. So if I move mass over here, I just move it down below. Well, now I have a formula that I created from my free body diagram and my Fnet equation that can solve for acceleration. So my force applied is 100 newtons. My force of friction is 20 newtons. And my mass is 10 kilograms. 100 minus 20 is 80. Divided by 10, we have 3 sig digs in the question. So it'd be 8 meters per second squared. Normally you would want a direction, but the question just asks for the magnitude of the acceleration. So just 8 meters per second squared is good enough for this. So I want you guys to try a board question. So I have Rick, and I have Dwayne pulls on a rope. So Dwayne pulls with 80 newtons of force. Rick pulls with 120, as shown in the picture. The rope has a mass of 2 kilograms. Draw a free body diagram. Calculate the acceleration of the rope. So try it on your own. Pause the video and see if you can do it. So here's my rope. This is force applied by Rick, which is to the left, which is bigger, is 120 newtons, and then force applied by Dwayne is smaller, which is 80 newtons. So from this, I can write my F net equation. F net is equal to, I'm going to make this positive, this negative. I usually like to make positive the winner, the direction that's bigger. So I'm going to say force applied by Rick is positive, and then force applied by Dwayne is negative. Okay. So I'm trying to find acceleration, so I can break this down into MA. Force applied by Rick is 120 newtons. Force applied by Dwayne is 80 newtons. And if I move mass down here, right, the mass of the rope is 2 kilograms down there. So 120 minus 80 is 40 divided by 2, which means 20 meters per second squared is the correct answer to the right number of sig, or no, we have 1 sig dig. Oops, that's a typo. It should be 2 sig digs. But anyways, and you also need a direction because it's not asking for the magnitude. So Rick is to the left, so you could either put to the left or you could put towards Rick, would be the best way to answer that question. And that's how you do that. So let's step it up a little bit more and use some stuff from the first half of the unit. So we have 100 Newton forces applied to accelerate a 20 kilogram box along a horizontal sidewalk where the kinetic coefficient of friction between the box and the sidewalk is 0.4. Determine the magnitude of the box's acceleration. So this steps up a little bit, but we still start the same way. Okay. So we'll start with our free body diagram. It says we have a 20 kilogram box and we have a 100 Newton force that's applied to it. It doesn't give a direction, so I'll just make it to the right. And it says that there's a force of friction, but it doesn't tell us what it is. All it gives us is a coefficient of friction, not a force of friction. And we only draw forces in free body diagrams. So if we want to find the acceleration, well, we can use an F net equation. I'll make this positive, this negative. So we have force applied minus force of friction, exactly the same as we did before, but now we're going to break it down just a little bit more. We can break this down into mass times acceleration. This we don't want to break down. But we can also break down our force of friction, right? We can break this down into mu Fn. We already know that. So Fn, what is that? Well, Fg, force normal like that. We know that these are equal and opposite. So Fn is equal to Fg. Oh, and we know that we can break Fg down into mg. So force normal is equal to mass times gravity. So I can break this down once more, like that. So we're trying to find acceleration. So if I move mass under here, it doesn't cancel out. So don't cancel it out. Well, we have everything we need to know now. So our force applied is 100 newtons. Our coefficient of friction is 0.40. That was given in the question. Our mass is 20 kilograms. Our G is 9.81 meters per second squared. And our mass is 20 kilograms. So if I plug that all into my calculator, this is how I would type it in. So at the top I do brackets. I do 100 minus, and then I do another bracket. 0.4 times 20 times 9.81. And then I double bracket it for the top, and then I divide it by 20. Oops. 20, close my bracket. and I end up getting my acceleration in, we have 2 sig digs, so our acceleration is 1.1 meters per second squared, and it just wants to know the magnitude, so that's good enough as an answer. So let's try a board question like that. Okay, try this on, pause the video, try this on your own, and see how it goes, and I'll go through it right now. So a force of 155 newtons is applied to a 5 kilogram moving accelerated object. The static coefficient of friction is 0.88, and the kinetic coefficient of friction is 0.7. So because it's moving, we want to use the kinetic coefficient of friction, not this. Determine the magnitude of the acceleration of the object. Okay, let's try that out. So we'll start off with the free body diagram. We have a 5 kilogram object. There's a force applied of 155 newtons. And there's friction, which we don't know. And we can write an F net equation. And our F net is equal to our force applied minus our force of friction, because this is positive, this is negative, because this is bigger, so I'm going to make that positive. We break this down into MA. We break this down, well, we don't break that down, and this we break down into UFN, and we also know that force normal is equal to force of gravity, and force of gravity equals mg, so I can break that down into mg. Okay, we move our m over here, and we can plug in our stuff. 155 newtons minus our coefficient of friction we want to use is 0.70. It's a 5 kilogram object. G is 9.81 meters per second squared. And our mass is 5 kilograms. So our answer is going to be 155 minus 0.7 times 5 times 9.81. Divided by 5. And we get our acceleration to be, we have 2 sig digs. It wants to know magnitude, so just 24 meters per second squared is a good answer. Okay. So I have one more board question here. A 150 kilogram car is traveling 26 meters per second when it sees a baby duckling on the road. The car screeches to a stop. The acceleration during the 7.45 meter per second squared trip is... So I want you to draw the free body diagram of the forces acting on the car as you screech to a stop. Okay, try that right now. Pause your video and I'll go through it now. So I'm sure everyone agrees. Everyone usually agrees. So this is my car here. We have a force of gravity, force normal. Don't really need those. But then we have a force of friction as it screeches to a stop. Most people agree on that. Where students get this wrong is with the force applied, right? Some people have a bigger force applied. If the force applied is bigger, well, what's happening? Well, that means that the car would be accelerating. So I always tell students that there are varying degrees of psychopath to this question. This is my baby duck here. So students who drew a free body diagram like that, well, you're accelerating towards the duck. You're trying to hit it even faster. So that's kind of messed up. Here, some people draw it as smaller, right? But remember, right, just like that question that we just did, an object in motion stays in motion. It doesn't need a force acting on it. So if the car is already moving, it doesn't need that force applied. So the correct answer is not having a force applied, where my F net is equal to my force of friction. That's your free body diagram. So let's do the second half of this question, see if you can get it. Find the coefficient of friction between the tires and the road now that we have the right free body diagram. So pause it again, see if you can do it. Okay, my F net is equal to MA. My force of friction is mu Fn. Fg equals mg, force of normal equals force of gravity. So we can break this down to mg. And the mass of my car actually doesn't matter. We can cancel those out in this situation. So if I want to find the coefficient of friction, I move that over. So it's just acceleration divided by g. So my acceleration is 7.45 meters per second squared. My g is 9.81 meters per second squared. And if I go 7.45 divided by 9.81, I get my coefficient of friction to 3 sig digs is 0.759, nothing, no units. 0.759 is my answer. Okay, that's how you do that question. So here is Newton's third law, which is the last of Newton's laws. So we have, for every force, there's an equal and opposite force. And people are very familiar with this. For every action, there's an equal and opposite reaction. But people don't actually know what it means or what situation it applies to. So the best way to see this is in space. So I have 2 different videos for you. So this is a real astronaut in space, and he does a nice experiment showing Newton's third law with the equal and opposite force. And then this video here is from the movie Gravity. And you can see a really nice Newton's third law as Sandra Bullock throws the fire extinguisher. And this last one is the best place you can see it on Earth with a gun and recoil. So they're shooting an elephant gun. They're not shooting an elephant, but they're shooting an elephant gun, which has enough force to take down an elephant. And yeah, it's got a big recoil on it, and that's from Newton's third law.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use 2 similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
tight, eh?
Don't drop the gun. Whatever you do, don't drop the gun.
Yeah.
That means it's gonna kick like a motherfucker.
Yeah, some guy was
But
scared.
hold it tight.
Woo!
So when you shot the gun, what were the two forces? So when you're talking about Newton's third law, you'll start to notice a trend. So there's one force, which is the force of the gun on bullet, and that's going to be equal to an opposite, so a negative direction of the bullet on the gun, right? The gun exerts a force on the bullet, and the bullet exerts a force on the gun, and that's why the gun goes backwards. So why does the bullet kill the person or the elephant or whatever messed up thing you're shooting, but the gun doesn't? Well, that's because when you have the gun, it has a bigger mass, right? We break this down into MA, we break this down into MA. The forces are the same, but if we have a smaller mass, like with our bullet, we have a bigger acceleration. And if we have a bigger mass, we have a smaller acceleration. That's what that's saying. Okay, so when a car crashes into a wall, what are the two forces? Well, let's use the same idea, right? We have the force of the car on the wall, and we have the force of the wall on the car, right? Those are the equal and opposite forces. It's not going to be force applied, but it's always car on wall, wall on car, gun on ball, ball on gun. So this is kind of a weird one. So when gravity pulls a ball to the ground, what are the two forces, right? So if I show you here, if I drop this pen, gravity makes it fall. So what are the two forces? What are the two Newton's third law forces acting on it? Well, they can't be different things, and we have to follow the same pattern. So there's a force of gravity of the earth on the pen, which is pretty obvious, right? The earth pulls the pen towards it. But what's not so obvious is there's a different force of gravity of the pen on the earth. The pen is actually pulling the earth up towards it. Well, why doesn't the earth all of a sudden feel like it moves every time we drop something? Well, because the mass of the earth is so big that the acceleration is zero. It's nothing. It's so much bigger than the pen that it doesn't even affect it. So that's why we don't all of a sudden feel that we're pulled up. So I have a question here. If you got 7.5 billion people in the world to jump at the same time, and each person pushed down with the same average force of 1,500 newtons. So there's some like old people and some babies on this. So we'll say the average is 1,500. So what would the acceleration of the Earth be? So we all go to Australia, and we all stand on this, and we all push down. Could we accelerate the Earth? Well, the answer is no. We couldn't. We wouldn't have a big enough force because if you took the mass of all the people on the Earth, right? So if you took 7.5 billion, which is times 10 to the 9 people, and let's say the average person is even 100 kilograms, which I think is like way, way, way higher than what the average mass would be. That'd be like 200 pounds. But so if I go actually let's clear this. 7.5 billion, which is times 10 to the 9, and I multiply it by 100, well, that's the mass of all the people on the Earth, right? The mass of the Earth is 5.97 times 10 to the 24, which is, if I divide it by the mass of all the people on Earth, that's how much bigger the Earth is than the mass of all the people. That's how much bigger the mass of the Earth is compared to all the people. So the answer is no. You need similar size masses, like with that astronaut, the two astronauts. When you have the person and the basketball, it doesn't work as well. Let's talk about free fall. So all objects allowed to drop with gravity being the only force acting on it, are said to be in free fall. And all objects in free fall will accelerate at 9.81 meters per second squared. So in physics, we can sometimes ignore air resistance. And we can ignore air resistance if the shape of the object is really aerodynamic, or if it's not moving very fast. But when we start moving faster, right? Wood has a greater air resistance force, sticking your hand out the window of a car traveling 110 kilometers an hour or putting your hand up as you walk, right? It's the same hand, but when you're walking, you feel no air resistance. If you're moving super fast, well, you feel a lot of air resistance. So air resistance increases the faster you move. So I'm going to show you a little demo here. You can actually see my face in this one here. Hello. I have two different balls here. So one of them is a steel ball and one of them is a wood ball. This one's really light, this one's really heavy. If I take these objects and I drop them at the same time, they hit the ground at the same time. Now, and this camera's not great, so I'm sure you won't be able to see it very well, but if you just listen for it, one noise. They hit the ground at the same time. So why do they hit the ground at the same time? Well, all objects accelerate at the same rate. This has the same acceleration as this. But if I switch up my objects, so now I'm going to keep my wood ball and I have a sheet of paper. If I drop them, well, they don't hit the ground at the same time anymore. Why? Well, they have different shapes, and air resistance plays a bigger factor in the sheet of paper than it does in the wood ball. But if I make the shapes so they're similar, I'm just going to use a different sheet of paper because I don't want to mess up my formula sheet. So if I have a different sheet of paper here, and I have the wood ball, but I make them similar shapes, and I make them super tiny, so I'm going to compact this as small as possible, like that. So I have two similarly sized objects now. It doesn't matter their mass. They'll all hit the ground at the same time. And I drop them now. They hit the ground at the same time. I hope you can see that on the camera. So air resistance affects different shaped objects and different massed objects differently. So the way we look at this, the way we analyze this is by using the term terminal velocity. So terminal velocity is the greatest speed an object can fall when frictional forces equal gravitational forces. So if you think of someone jumping out of a plane, so this is someone jumping out of the plane, initially they're going to be in free fall because the force of gravity is the only thing acting on them. Sorry, I'm going to draw that again. The force of gravity is the only thing acting on them. But as they move faster, what's going to happen is this force of friction is going to increase. The force of friction is going to increase. The faster they go, the force of friction is going to get bigger and bigger and bigger. And at a certain point, force of gravity equals our force of friction. And if they equal each other, if this is our free body diagram and they're the same forces, what does that mean? Well, it's going to fall with a constant speed. And that's what terminal velocity is. So the reason that my paper takes longer to hit the ground because it hits the terminal velocity really quick. If we have a lot of friction and not a very big mass, not a big force of gravity, it reaches terminal velocity almost instantly. While the more aerodynamic ball, well, it doesn't have as much friction, so it doesn't reach that terminal velocity. So terminal velocity is the greatest speed an object can fall when your frictional forces equal your gravitational forces. So if you jumped out of a plane, initially you'd be accelerating, but at a certain point you would stop accelerating. Here's a video that shows what happens if you get rid of air resistance. So this was filmed on the moon, and they took a feather and they took a hammer and they dropped them, but there's no air resistance because there's no atmosphere on the moon, and you can see that everything falls at the same rate.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So I want to explain what 9.81 meters per second squared mean, because lots of people are weirded out by the squared. So acceleration is your change in velocity over change in time. So what that means, what 9.81 meters per second squared means, is that my velocity will change by 9.81 meters per second. That's what its change will be for every 1 second that it falls. So after I drop something, so whenever I say drop, it means it starts off at 0 meters per second. So how fast will it be going after 1 second? Well, if it falls for 1 second, then it's going to be going 9.81 meters per second after 1 second, meters per second squared. After 2 seconds, well, it's going to gain another 9.81 meters per second. So it's going to be going 19.62 meters per second. How far after 3? Well, it's going to gain another 9.81 meters per second. So if it gains another 9.81 meters per second, it's going to be, I forget, I can't do this in my head. So if I go 19.62 plus another 9.81, then I end up getting 29.43 meters per second. So that's what 9.81 meters per second squared is. No matter what the object is, no matter what the mass, if we ignore air resistance and force of gravity is acting on it, it's going to gain 9.81 meters per second every second it falls. If it falls for 10 seconds, then it's going to be going 98.1 meters per second squared, because this is going to be 9.81 plus 9.81 plus 9.81 plus 9.81 10 times, or 9.81 times 10, and that's how fast, oops, not squared, that's how fast it's going to be going, 98.1 meters per second. So physics principle 1 is use time any time there's a net force that is not 0. So which formula you use depends on which value is missing from the question. These are the 5 formulas that we'll be using for this, where A is acceleration, V is velocity, T is time, VF is our final velocity, VI is our initial velocity, and D is our displacement. So these formulas are all found under the first section, which is speed, distance, time, and acceleration. So you can find them up here. This is V equals D over T, which we use as physics principle 0. And then these next 5 are all physics principle 1 stuff. Okay, so what I mean by you use which formula depending on which value is missing from the question. So this one, you can see it has all the variables except for distance. This one has all the variables except for final velocity. This has all the variables except for initial velocity. This has all the variables except for acceleration. And this one has all the variables except for time. So depending on which one is missing, that's how you know which formula to use. So let's do an example. A rock is dropped from the top of a bridge. It takes 3.02 seconds to reach the water directly below it. Calculate the height of the bridge above the water and neglect air resistance. So how you do these questions is you always start off with VI, VF, DAT, or if you're cool, you can VI, VF, DAT, right? So you fill in all that you need to know, and you need 3 of 5 to be able to do these questions. So the question originally says the rock is dropped from a bridge. It takes 3.02 seconds. Awesome. We know our time is 3.02 seconds, but that's the only number it gives us in the question. Well, it says to neglect air resistance, and if something is dropped and we neglect air resistance, we know that our acceleration is 9.81 meters per second squared. It also says that it's dropped, and if it's dropped, our initial speed is 0 meters per second. So we want to calculate the height of the bridge. So that means that our final velocity is missing. So we want to select a formula without final velocity. And the only formula without final velocity is D equals VIT plus 1/2 AT squared. So this one looks confusing to rearrange, but if our initial velocity is 0, if I go 0 times 3.02, that's 0. And 0 plus, well, it's just whatever that is. So if ever your initial velocity is 0, then you can get rid of that, and it makes it a nicer formula to rearrange. We don't need to rearrange it because we're trying to find distance, so we just have to go 1/2, 9.81 meters per second squared, and our time is 3.02 seconds, and we square that time. So typing this into my calculator, what I would want to do, so I don't type in 1/2, I type in, oops, I don't need a bracket, there's nothing on the bottom. So instead of 1/2, I type in 0.5, and then multiply it by 9.81, and then multiply it by 3.02, and I square it like that. And I get the height of the bridge, I have 3 sig digs, is going to be 44.7 meters. Okay. In terms of positives and negatives for this question, so if this is my bridge, the distance is down, the acceleration is down, and time doesn't have a vector with it. Because everything is down, I say everything down is positive. So this is positive as well, but height would just be a scalar quantity. So I don't really worry about negatives or positives with this question. Okay, let's try another one. So a baseball pitcher throws a fastball at a speed of 30 meters per second. During the throwing motion, the pitcher accelerates the ball 3.5 meters, starting from when his arm is extended behind his body to a point where the ball is released when his arm is fully extended in front. Calculate the magnitude of the average acceleration of the ball during the throwing motion. Okay, so for this one, it's just a pitcher starting here, throwing the ball. That's all it's talking about. So we have VI, VF, DAT is how we want to start this question. So it says that the ball moves 3.5 meters, it accelerates 3.5 meters, and it says he throws a fastball of 30 meters per second. So that's going to be my final speed, is at 30 meters per second. If it started, well, the ball starts from 0, right? When the pitcher winds up, he's starting it's to 0, it goes to 30, and it does it in 3.5 meters. We want to find the acceleration, so that means that time is missing. So we want to select the formula without time. And the only formula without time is VF squared equals VI squared plus 2AD. Okay. If our initial velocity is 0, 0 squared is 0, well, it's much nicer to rearrange like that. We want to find our acceleration, so we can move the 2 down below, we can move the D down below, and we can solve for acceleration. So it's just 30 meters per second squared, 2 times 3.5 meters. So when I type this into my calculator, I would go 30 squared on top, and then on the bottom, I would go 2 times 3.5. So the acceleration is, and I have 3 sig digs, 129 meters per second squared. I don't need a direction because it's just asking for the magnitude of the acceleration. So this question is a little bit trickier. A ball is dropped and hit the floor at a speed of 4.1 meters per second. The ball compresses and reforms to spring upwards from the floor at 3.8 meters per second. The time from the ball's first contact to when it left contact with the floor is 0.11 seconds. Calculate the ball's acceleration on its contact with the floor. So whenever a question's tricky, it's good to draw a picture. So this is the ball on its way down, and it's going 4.1 meters per second. The ball squishes, compresses, and then it springs back up at 3.8 meters per second. So we can use VI, VF, DAT. So they told us it did this all in a time of 0.11 seconds. Our initial is 3.8 meters per second. Our initial is 4.1 meters per second, and our final is 3.8 meters per second. We want to find acceleration, and we don't have distance. So This is a mistake that a lot of students would make, is they just fill it out like this. But because this is going down and this is going up, we need to assign positives and negatives to down and up. This is going up, I'll make it positive, down is negative. It doesn't actually matter which one is which, you just have to assign one of them. So this is going to be negative, and this is going to be positive. So we want to use final minus initial all over time. My final is positive 3.8 meters per second. My initial is 4.1 meters per second negative, and my time is 0.11 seconds. And you can see this negative makes it positive, which changes your answer quite a bit if you didn't put that on there. So on top we have positive 3.8 minus negative 4.1 divided by 0.11. And we get to 2 sig digs, we get 72 meters per second squared. It's positive. We need to include direction, which is up, because it's not just asking for the magnitude, so that would be our final answer. Okay, so let's try a couple board questions. So pause the video and try these on your own, and I will go through it right now. So a fish is dropped into a river from the top of a 12-meter tall bridge. Determine the time it takes to hit the water. So you want to start off with VI, VF, DAT. This is the fish's drop, so that's 0 meters per second. It's in free fall, so 9.81 meters per second squared. And it says that the bridge height is 12 meters. We want to find the time, so we don't have final velocity. So the only formula without final velocity is this one right here. And because our initial velocity is 0, get rid of that. So we have d equals 1/2 at squared. So we want to find time, so we have to rearrange it. So I move 2 up top, I move a down below, and square root both sides to get rid of that. So it just ends up being 2 times 12 meters divided by 9.81 meters per second squared. And I have to square root my answer. And when I do that, 2 times 12 divided by 9.81. And then I square root my answer. And I get the time it took to be 1.56 seconds, but we only have 2 sig digs, so 1.6 seconds would be the correct answer. So this is our last board question, so let's give this one a go. A fish is dropped into a river from the top of, wrong one. A child rolled a fish up a hill. The fish had a velocity of 1.8 meters per second up the hill. After 6.5 seconds, the fish's velocity was 2.3 meters per second down. What's the fish's acceleration? So let's draw a little picture of what's going on here, just to better sort this out, and make sure you pause the video and try it on your own. So the fish is initially rolling up the hill. This is my fish. It's rolling up the hill at 1.8 meters per second, and then it's rolling down the hill at 2.3 meters per second. So we VI, VF, DAT this. Initially, it's 1.8 meters per second. Finally, it's 2.3 meters per second, and it does this all in a time of 6.5 seconds. But this is going up, this is going down. So we need to say that one of them is positive and negative. It doesn't matter which one is which. So I'll make this positive, this negative. So initially it has a positive velocity, and finally it has a negative velocity because it's down the hill. We use acceleration equals final minus initial all over time. So my final speed is negative 2.3 meters per second, and my initial speed is positive 1.8 meters per second. I divide it by a time of 6.5 seconds, and when I type this into my calculator, negative 2.3 minus 1.8 divided by 6.5, I get an answer of negative 0.63. We have 2 sig digs, meters per second squared. And it's not asking for the magnitude, it's asking for the acceleration. So negative means down the hill, according to what I've put here. So down the hill would be my correct answer, to the right number of sig digs with my direction in there. So this is your homework. There's quite a bit of it. This is the most homework you have all year, but you don't have your unit exam for a little bit. So Chuck me through this and see if he can get this all done.